Cool. So thank you very much for all coming out in the middle of exam term. So a few general points before I begin. If there's a fire, don't look at me. I am not going to be your savior. If you have any questions at any point, please interrupt and ask. The point of this is for people to understand. And I think generally people at Cambridge do not ask anywhere near enough questions and things, so please do, shut up. Timothy is the exception from that rule, he does not count. And yeah, I'm also going to be putting a feedback form online after this, and I would really, really like to hear just any things I could improve, any things that went well, because I find doing that kind of thing really hard, and calibration is incredibly useful. And without further ado, I will begin with, do you actually have a question?
Genuine question, actually. 1A students, we'll just have to make a decision whether or not this is likely something that one of these students already know and is easy, versus something that could actually value everyone, or what's your opinion on that scale?
Let's see. Questions which are just can you define this thing? Go for it. Questions that are will take a while to answer, probably not, would be my general advice for 1A students. But kind of, I'm going to try to not assume anything that wasn't actually in the course. So if you don't think it was in the course, ask away. Anyway.
So could you write slightly bigger than you did in the
sure.
linear algebra?
That's a perfectly valid question. I will make an effort to do so. Okay, so chapter 0, the introductory chapter, is stuff you really should have learned in first year groups, but probably didn't, as you had a really good supervisor. So first off, I think, so this is a talk about algebra, and a really important question to answer when you're doing algebra is what are you doing, what are the things you're defining, and why are you defining them? So I want to just talk briefly about why do we study groups at all? So kind of the point of algebra as a field of maths is you take some structure you want to study, like symmetries, and you define a really, really short set of rules which everything you want to study satisfies, and you hope that these set of rules kind of capture everything interesting about this. And the point of algebra is just, I'm going to only study these rules rather than the underlying structure I care about, and try and build a really deep understanding and an intuition and toolkit. And then whenever you see something like this in the wild, you hopefully already have this really deep and beautiful understanding to use. And groups are basically applying this core idea to the notion of symmetries. So a symmetry I'm going to define as a function that preserves something interesting, like say a transformation of the plane that preserves a triangle, so rotations and reflections. And kind of anything which preserves some structure of my space. If I do nothing, everything is preserved, so the identity is always a symmetry. If I do something backwards, and it preserved by structure, doing it backwards preserves it, so symmetry is reversible. If I do two things that preserve the triangle, then doing them both in succession still preserves the triangle, things are closed. And these functions, they're associative. And that's why the group axioms are what they are. And kind of the beauty of groups and the beauty of algebra in general is that these 4 rules aren't just necessary to be a symmetry, they kind of describe everything interesting about them. And the entire point of group theory is trying to study what that means in the abstract, and just studying something where all you know is satisfy these rules. Okay, so that's not awful, but why do you care about groups? The first thing I want to address, which is a really important object from 1A groups, is conjugation. So conjugation you kind of see defined as just, you take H and you stick H and you kind of stick this symbol G around it, and this kind of seems like unmotivated magical trickery. But this is actually an incredibly deep and important operation in groups. And I think this is most clearly demonstrated with permutation groups. So if you take something like 1, 2, 3, and you conjugate it by sigma, then it goes to the permutation of sigma 1, sigma 2, and sigma 3. So it's kind of exactly the same cycle, but now I'm permuting the set sigma 1, sigma 2, sigma 3, rather than the set 1, 2, 3. It's kind of doing exactly the same thing, but I've swapped my labels around. And that's actually what permutations do in general. So groups are about symmetries. So we understand a group by looking at a set that it acts on, that it permutes. And so if I have some symmetry R, and I conjugate it by some other symmetry S, then this thing sends a point R of X, sends a point S of X to a point S of R of X. So it's doing exactly the same transformation, but we've now changed our labels. We put an S in front of everything. And so kind of the point of groups and the point of symmetries is that we're studying this function, and we just give it a space to act on and see what it does. And the point of conjugation is the conjugate of a group element does exactly the same thing. It's just acting on a different set. So, and this isn't just kind of some gibberish. This is actually really, really useful for understanding conjugation. So let's take a geometric example. I want to study the operation rotate by 90 degrees. And I want to also study the operation kind of reflect in a line. So what does S conjugated by R look like? That's a reflection on the plane where you relabel every point by rotating by 90 degrees. And so you figure out what that is by saying, I'm going to rotate space by 90 degrees, and then it's just the same reflection. So this is a reflection in the line rotated by 90 degrees. And this is kind of the picture you should always have in your mind when you're thinking about conjugation. You're just relabeling space. The second really important thing from 1A groups that I think there's a really deep intuition to understand is normal subgroups. So you taught normal subgroups as just K is normal if anything you conjugate by is the same as K. Sorry, if you conjugate by anything, you get the same group out. And you kind of think about this and engage with this as just a bunch of algebraic manipulations. But the point of normal subgroups is that we don't really care about a group that satisfies this weird algebraic property. What we care about are the structure of our group. And related to that, we care about functions between groups that preserve structure, so homomorphisms. And a natural thing to care about when you have a homomorphism is what things does it send to the identity, because the identity is the one interesting element of our group. So we define the kernel as things that get sent to the identity. And the entire point of normal subgroups is that all kernels satisfy this property. And if you have a group that satisfies this property, it actually happens to be the kernel of some homomorphism by looking at cosets. And so the kind of key point is that normal is the same thing as kernel. And this is kind of a microcosm of abstract algebra. We care about this abstract notion of things that are kernels. All of them satisfy this one rule. When you conjugate, you get the same thing back. And it turns out this is all you need. And this is really important because it means that every time you ever have a question where you need to engage with normal subgroups, you should always be thinking about them as the kernel of some homomorphism. And every time you ever try and engage with quotients, you should think about the quotient as the image of a homomorphism. So just to take one example, if I care about the groups GL2, so matrices that are inversible, and SL2, matrices with determinant 1, this is the kernel under the homomorphism det. And so if I care about this quotient, I should always be thinking about this as the image of the matrices when I apply det, so the reals. And if you start trying to think about these as cosets, we're just going to go catastrophically wrong because cosets are kind of fiddly and messy. And the point of cosets is they formalize our intuition that normal subgroups are about kernels, and then we can just forget about cosets. Cosets are a tool to build our homomorphism. and then we only think about the homomorphism. And the point of the first isomorphism theorem is it's a way to kind of go from this intuition, normal is the same as kernel, to a thing you can actually like deal with and engage with, because it formalizes its intuition to you. And one thing in maths I think is really worth paying attention to is just what theorems are important, not because they're hard to prove, but because they formalize deep and really useful intuitions. So yeah, that's the end of the intro section, just things you really should have learned in 1A groups. Now I'm going to talk a bit more about the groups you actually, like how you actually engage with groups in groups and group modules, and how you build on these ideas. So, chapter 0, 1B groups. Chapter 1, 1B groups. So, the first interesting thing we do with groups in groups and group modules is we study these like bonus isomorphism theorems. And, okay, so first off, we have the second isomorphism theorem. This is not actually a very interesting theorem, and I basically never seen it used, but there's like a kind of cute idea. So, the second isomorphism theorem says, if H is a subgroup of G, and K is a normal subgroup of G, then 8K, so the subgroup where you take something in H and compose with something in K, quotiented by K, is the same as H quotiented by H intersect K. So what's actually going on here? So this is a statement about normal subgroups, and it's a statement about homomorphisms. So we understand it by just thinking in those terms. So we have a normal subgroup, which means we have a homomorphism. Phi goes from G to G mod K. That's like the entire point of normal subgroups. And the interesting thing we want to study is what happens when you have a subgroup of the thing you're taking your hom from. And the point of this is that homomorphisms preserve subgroups. So if you look at the image of H under this map, you get a subgroup out of the end. And there are two different ways we can study this subgroup. We could think of this as like something that comes from phi, or we could think about it as something that comes from phi restricted to H. So we can kind of define two different maps, and both of them contain this image. And so the thing we want to study is what things in this map get sent to phi of H, and what things in this map get sent to phi of H. So the things in G that get sent to phi of H are things in H, something that gets sent to 0. So HK. And what's the kernel is just the kernel of phi in G. So mod K. And what things in here get sent to phi of H? So everything gets sent to phi of H, that's kind of the point. And the things that get sent to 0 are the things in K that are also in H. So this is also the same as H mod H intersect K. And like, that's the point of the second isomorphism theorem, just subgroups map to subgroups under a homomorphism. And you can interpret things in two different ways. And every time you can interpret things in two different ways, you get a homomorphism out at the end. So yeah, as I said, that's not like a super interesting theorem. The third isomorphism theorem I actually think is a really interesting and deep theorem, because it formalizes a different deep intuition about what homomorphism is actually about. So the kind of key point of the third isomorphism theorem is that kernels, sorry, is this writing large enough or should I make it bigger? Cool.
This size is good, but it's quite light.
Fair enough.
Oh, how do you do that?
Brute strength. Kernels represent the loss of information. So what do I mean by this? I mean that when you have a function, when you have a group homomorphism, you take in a group and then it kind of sends some things together. Like for example, if you have a function which takes G and it sends everything to identity, it blurs it all together. And the way to think about the information you lose is to say which things get sent to the same thing. And phi of A equals phi of b, if and only if, like, AB inverse is in the kernel. And this is like a deep point, because it means that if you have two normal subgroups, where one is like within the other, then the homomorphism where J is the kernel loses like strictly less information than the homomorphism where K is the kernel. And this is important because it tells you that if you have like a map from G to G mod K and a map from G to G mod J, this map loses strictly less information than this map, and so you can factor it through. Like there is an arrow you can put in here so that these two maps are the same as this map. And you prove this by like fiddling with cosets. But again, fiddling with cosets is how you show you're allowed to do this. Not the thing you should actually have in your mind is the important point. And for any category theorists in the room, this is what's called the universal property of the quotient, but that's not really important. So why is this interesting? This is interesting because, well, so it gives you the third isomorphism theorem. Like, what does this map look like? This is a map which has kernel K mod J, and it sends G mod J to G mod K. So that is literally the third isomorphism theorem. And you can kind of think of it as just fractions work. But the deeper point behind this is that, like, maps, like, if you ever have nested normal subgroups, that means maps always factor through. And the even deeper point behind that is that this means I can understand the structure of G mod J in terms of the structure of G. Like, any function from G mod J to something else corresponds to a function from G to that thing. And any function from G to something else that sends J to 0 corresponds to a function from G mod J to that. Like, I can talk about this in terms of that and vice versa. And like, that's really important. And it means that there's a correspondence between normal subgroups of G that contain J and normal subgroups of G mod J. And the kind of higher level point behind all of the stuff I've just done is that this wasn't really a statement about groups. This was a statement about like maps and kernels and maps that preserve structure. And all of the times I engaged with groups were just kind of messing with cosets, and that wasn't actually important. What was important was that, like, I had things that got set to 0. And like, that's why you get the exact same theorems with rings and modules, because it's not a statement about groups, it's a statement about functions. And functions are a language you can speak about rings with, you can speak about groups with, you can speak about homomorphisms with. In fact, this probably even true for like quotient topological spaces. If you have a continuous map which agrees on the thing you're quotienting by, you can always factor it through. So, is the recording going okay? Yeah. Cool. Yeah, and this is something I'm going to highlight again as like what I like to call an intuition path. It's a way of formalizing this intuition that this is how quotients work. Things factor through. And that's why you should pay attention to this theorem. If you're ever trying to think in these terms, use the theorem to formalize what you're actually trying to do. So that's like the most abstract part of the group section. Now we're going to kind of get our hands a bit dirty and engage with what the course actually tries to do with groups. So the first thing we study is, well, the first kind of big tool we develop for learning about groups is the notion of group actions. And the point of a group action is that groups are about studying symmetries. And the way to understand a symmetry is to like give it something to be a symmetry of, give it a set to act upon. And that's kind of a lens to study the group through. And so kind of the key point here is that step 1 should always be choose the right action. And that's kind of the key to just so many of the questions about groups you get in this course. And choosing the right action is hard, but I think in general there are 3 really, really useful actions. So G conjugating elements G conjugating subgroups and G multiplying cosets of a subgroup. And anytime you're kind of stuck with the regular action, just run through this list, and like 3/4 of the time, the thing you want is going to be on here. So now let's kind of try and specialize a bit more. So one really interesting object we study are P groups. So groups whose size are the power of P. And the reason these are interesting is by orbit stabilizer, the size of an orbit always divides the size of a group. And if the size of a group is P to the K, then the size of an orbit is always 1 or a multiple of P. And this means that, and we also know that orbits partition the set they act upon. So the size of the set you act upon is always equal to the number of fixed points mod P. And that's kind of the key result of P groups. And I'm going to actually highlight this. The kind of the entire point of P groups is they engage with fixed points. So let's try and think about what this actually means. Let's run through a list of actions and see which of them are interesting. So, yeah.
So what's X?
Sorry, X is the set the action is acting upon. So you have a homomorphism from G to the symmetries of X. If G was a permutation group, X would be the set of integers from 1 to n, for example. And thank you for asking that question. So let's just run through our list. So fixed points of cosets, meh, that's not really a thing. Fixed points of conjugation, that's another subgroup, that's kind of cool. But fixed points of elements is really interesting because the identity is always a fixed point of this. And the number of elements is a multiple of P. And so kind of the first intro result you get from P groups is that when you conjugate, you have a multiple of P fixed points. And you have at least one. So you have at least P fixed points. And a fixed point of conjugation is something that commutes with every element of the group. It's the center. And so that's why P groups have a non-trivial center. You just, the point of P groups are fixed points. And that's just a thing that immediately falls out when you think about fixed points. And that's incredibly useful for thinking about P groups. And the kind of deeper part of P groups is you get a bunch of cool theorems about them, like Cauchy's theorem, Sylow's theorems. And there's these theorems are kind of a bit magical. You have to come up with a really clever action, and there's often a few more clever ideas. But I just want to kind of highlight what the actions are and kind of why they're interesting. So Cauchy's theorem, it's about ZP acting on P tuples so that the product is the identity. This is a weird and magical action, but fixed points of this are elements of order P, and that's why Cauchy's theorem works. P groups are about fixed points. Sylow's first theorem, that's G left multiplies subsets of size P to the A. Here this isn't quite about fixed point because the thing that's acting isn't P group, but fundamentally this is a statement about modular arithmetic. Sylow's second theorem, and there's a few more technical details, but the point is here is a clever and magical action. Sylow's second theorem, P, a Sylow P subgroups, acts on cosets of Q, another one. And this is interesting because a fixed point of this tells you that Q is a conjugate of P and vice versa. And so fixed points, it's a P group, yay. And Sylow's third theorem is about P, a subgroup, or the actual group. acting on like the Sylow P subgroups by conjugation, and when P is acting, it's a P group, so we care about fixed points, and that's like the key idea of proving like the second bit of Sylow's third theorem. And yeah, I just want to highlight again, the way to understand these theorems is by kind of learning this action and why these actions are interesting. And these are hard to advance, but they also highlight the key point that P groups are about fixed points. So what next? We next care about simple groups. So simple groups feel a little bit weird, like groups that don't contain normal subgroups, or non-trivial normal subgroups. And if we're thinking about normal subgroups from the perspective of here is a group, when you conjugate by some magic elements, you get some magic outs. That just doesn't really seem to make any sense, like you have no understanding. But again, the point of normal subgroups is they're kernels of homomorphisms. So the point of a group that contains no non-trivial normal subgroups, it means there are no homs that have non-trivial kernel. What does that actually mean? It means, key point, simple, means that all homomorphisms are injective or trivial. So if it's trivial, the kernel is the entire group. If it's injective, the kernel is like nothing, the identity. And the point of a simple group is it has this magical property. And like this is an incredibly powerful constraint on what a group can be like. And again, all of this deep understanding comes because the point of a normal subgroup is it's about kernels of homomorphisms. So how do we actually engage with this? How should we show that how can we show that a group is simple? Or show that, say, there are no simple groups of order n, the sum n? The way to do this is by constructing homs and trying to find a hom which can't have this property. And how do you construct a hom? You take a group action. Like the point of a group action is it's a way to generate homs really easily, because a group action is a homomorphism from the group to the symmetry of whatever acts upon. Like the point of a symmetry is just the set you're acting upon is the integers from 1 to n, and it permutes those. And that just works in general with a hom. And we have my epic list of cool actions to take. But let's think a bit deeper. Like, how do you actually how do you ensure which action might work rather than brute force triangle them? So the next insight is homs, actions are homs from G to the symmetry group of the set you act upon. And symmetry groups are way more interesting the smaller this thing is. Like, there's trivially a hom from G to S size of G by just left multiplication. So if this is too big, there's nothing interesting there. Like, you have more and more freedom to fit random crap in there, the bigger this is. And so conversely, we want to choose an action with as small a set size as possible. And so if you ever have a question where you're thinking, I should be choosing the right action, look for things that are small to act upon. So how do you think about subgroups of small index? The index is the number of cosets. And so you should think about how G permutes the cosets of that subgroup. And why does looking at this actually tell you anything? Why does knowing this form exists tell you anything? The two most useful bits of the structure are that the size of G is at most the size of the group, and the size of G divides the size of the group. And additional cool thing, remind them that we're looking for homs, not for actions. And there's a natural hom from the symmetry group to just plus or minus 1 by taking the sign. And so we actually know that the image of G must be inside the alternating group, because we can just append on the sign. And so we can divide by 2 over here, because that actually goes into the alternating group, not just into the symmetric group. And the other source of things that are small is by using Sylow's theorems. So Sylow's theorems kind of just give you a bunch of rules you can bash through to like figure out what the size, how many Sylow of P subgroups there could be for each P. And if NP is small, then that's really interesting because, yeah, if NP is small, then like the size of is small, and so you should act on the Sylow of P subgroups by conjugation, because the point of choosing an action is hunting for small things to act upon. And so the way to, how to actually use Sylow's theorems, if NP equals 1, it's normal. If NP is small, act. And if it's big, then you just count elements. Like, you can't have too many subgroups. Like, if you have a group of size 100, you can't have like 1,000 subgroups of size 5 for obvious reasons. And so, anytime you ever want to use Sylow's theorems, just do one of these 3 things. And the reason if it's small you should act on it is that the smaller a set is, the more interesting acting on it is. So that's kind of all I have to say about groups. So I want to kind of run through the kind of key points and big ideas in there again. So groups are fundamentally about symmetries. And everything, like all your intuition about groups should kind of fit into that lens. Conjugation is a lovely, important, and natural operation because it's just relabeling the space you act upon. The point of normal subgroups and quotients is they're about studying Thms and images. And every time you ever need to engage with a quotient group, you should always think about it as the image of the relevant Thm, not as like cosets and fuckery. And P groups are interesting because they're about fixed points, and simple groups are interesting because it tells you that all Thms are either injective or trivial. And the way to understand simple groups is by hunting for actions, and this is how you hunt for actions. Are there any questions about groups? Yeah.
When you mentioned the universal property thing, could you elaborate how you can use that to actually learn things about G?
Sure. So the universal property I mentioned is that if you have like a map from like G to G mod K, and then another map from G to H, where H lives inside the kernel of this map, then it kind of factors through, because this map has lost exactly as much, has lost strictly more information than this. And the point of that is that, so the normal subgroups inside G mod K correspond to the functions you can take from G mod K. And those obviously correspond to functions from G to something else with K inside the kernel. And the point of this property is that if you've got a function from G to something else which has K inside the kernel, then it factors into a map from G mod K to something else. And so all of the structure of G which sends K to 0 bijects with the structure of G mod K. Does that make more sense? Cool. Great. So I'll take a 1-minute breather and then onto rings. Morning, doing okay, James?
Yeah, doing well. Awesome.
Oh. So G acts on some sense, and a fixed point of that action is something like ordinary slice method. It's something where G dot x equals x for every G. So like, say yeah, x is a fixed point of conjugation, because the density of conjugation by G is just x. Is that cool?
Yeah, I think
no worries. Okay, onwards to rings. So So rings are like way more interesting than groups, in my opinion. Because rings have two operations. They have addition and they have multiplication. And you get vastly more deep and messy and complicated structure when you have two different operations that can like interplay with each other. Unfortunately, this also makes rings like way harder and gives them like vastly more properties and ways to interpret them. And so that ring theory is both way more interesting and just way harder than group theory. In terms of kind of high-level maths, thinking about rings are incredibly useful for studying algebraic number theory and algebraic geometry, which are two kind of really cool but really hard areas of maths. If you want to learn more about either of these, there are part 2 courses on them. Number fields is the part 2 course about algebraic number theory. And I know a bit about number theory and nothing about geometry, so I'm basically entirely talking about how to use number theory. Okay, so that's not all about what we care about rings. One really important part of studying rings is kind of classifying them. So finding interesting properties and ways of thinking about them. And the kind of weirdness of groups, of rings, is we've added this new operation, multiplication. Like, addition is quite easy, it's just an abelian group, but multiplication is this thing we don't understand at all. And so the first ins for classifying rings is trying to come up with the nice properties multiplication could have. And so I think two really natural properties multiplication can have is injectivity, which is the same as saying R is an integral domain, because it's saying that if you have some non-zero b, if you multiply by any a, you don't get 0. Like, a map having no kernel is the same as it being injective. So the point of integral domains is it means that multiplication is injective. What's another cool property? Inversible. And that means that R is a field. So I think these are two really natural ways to classify rings, because they're just saying, what's a good property for our thing to have? Injectivity, invertibility. Let's just give those a name. And observe that this trivially tells you that a finite integral domain is a field, because an injective function from a finite set to itself is a bijection, it's invertible. That's all that's going on with that statement. And kind of all of the clever bits in the proof is just realizing that's what these two definitions actually mean. So the first difficult and messy object with rings are ideals. And that's going to be what I focus on in this section, because I think that there's a ton of depth to thinking about ideals properly. So I think there are 3 ways you can think about ideals. The first lens of thinking about ideals is it's just a set where x plus y is in I for any x in I, and r dot x is in I for any x in I. Just an unmotivated load of algebra you write down. And I think this is how a lot of people leave the course thinking about ideals. And this is a terrible way to think about ideals. It's use this if you need to do some trivial manipulation, but this is a really bad thing to reason about a problem. So just forget this. The second way of thinking about ideals, that I think is vastly more insightful, is that ideals are kernels. So please now pretend that I've repeated every single thing I just said about normal subgroups, because that applies perfectly to ideals. We care about Hms because we care about the structure of the ring. We care about functions that preserve structure. And so we care about kernels of Hms. And it turns out that all kernels of Hms satisfy these properties. If two things map to 0, their sum maps to 0. If something maps to 0, that times anything maps to 0. And so all kernels satisfy this. And the point of quotient rings and cosets is just pointing out to you that anything that satisfies these properties is the kernel of some homomorphism. And so, just as with normal subgroups, the way to think about ideals should almost always be, it's the kernel of some homomorphism. And the way to think about quotient rings is they're the image of some homomorphism. And just the reason you get like this long list of isomorphism theorems again is what I was saying earlier about universal properties. The point of like kernels and quotients and homomorphisms is not that they're about groups or that they're about rings, it's that they're about functions and things that get sent to zero. And that language applies perfectly to rings and ideals, and that's why you get the three isomorphism theorems again. And they formalize exactly the same intuitions. They're like really, really analogous. The one slight weirdness is that ideals aren't subrings, unlike normal subgroups, but they share this core property of being kernels, and that's what matters. So let's think about how this lens of thinking actually helps. So the intersection of two ideals is an ideal. Why is this? You can prove this property holds, but a much more interesting way is to observe that if you have the Hom that sends R to this, where like phi sub I is the thing with kernel I, phi sub j is the thing with kernel j. This is zero if and only if both entries are zero, which means something's in I and it's in j. And that's why the intersection of two ideals is an ideal, because you just construct a function. Why we have two kind of really important definitions of ideals, prime and maximal. And you can define, like, say, I can define a prime ideal as if x and y are in your ideal, then x is in your ideal or y is in your ideal. But that's a boring definition. And a much better definition is we really care about kernels, and ideals are about functions. So I say an ideal is prime if it's the kernel of R to an integral domain. And if you just chase through the definitions, mapping from being the kernel of a map from R to the integral domain means two things multiplied to something that gets sent to zero, if and only if one of them gets sent to zero. And that's what a prime ideal is. That's why we care about prime ideals. And the point of a maximal ideal is it's the kernel of a map from R to a field. Because if we try to think in terms of ideals, a field is a ring where the only ideals are like the zero ideal and the entire thing. And so the only time there's a map where the only ideals in the image are zero on the entire thing is if there's no bigger ideal. And so maximal ideals are about Homs of fields. Prime ideals are about Homs of integral domains. And these are things we care about, because these are the two like really natural ways to think about rings. And I think that's a much better way to define them. An additional cool note is that if we define fields solely in terms of ideals, like where there is like the zero ideal or the entire thing, and those are the only ideals we care about, that's kind of exactly the same definition as a simple group. And so one cool way to think about fields is that the only Homs from a field of another ring are injective or trivial, which is just quite a cool ordinal property, though a lot less useful than some groups, sadly. So let's take another example of where thinking about ideals in this lens and trying to formulate things in terms of ideals is really, really useful. So let's think about Noetherian rings. So a ring is Noetherian if all ideals are finitely generated. So you can just pick a few things, and then every element of your ideal is a linear combination of those. And why is this an interesting property? So you can show that this is equivalent to so like it's Noetherian if and only if all infinite ascending chains of ideals is eventually constant. So like, if you just keep doing this, eventually all ideals have to be the same. Why is this the same notion as being finitely generated, all ideals being finitely generated? It's the same notion because if you had an infinitely generated ideal, you could just keep choosing a building up a generating set. And the ideal generated by the first n elements would be the nth thing in a chain. And you can kind of prove by some fiddling that these are the same idea. But I want to try and convince you that this is actually a much more natural way to think about Noetherian rings. Because, so, these are nested ideals. And we know from, like, the third isomorphism theorem for groups and the third isomorphism theorem for rings, that if you have one ideal inside another ideal, you can take a homomorphism from R to R mod I1, a homomorphism from R to R mod I2, and it like factors through, because this hom loses strictly more information than this hom. And this is interesting, because it tells you that having an infinite chain is the same as having an infinite chain of surjective functions. Surjective just because maps from R to R mod something else is surjective. That's what the first isomorphism theorem says. And so you can think about a ring being Noetherian as saying there is no infinite chain of functions that isn't eventually like just constant, just isomorphisms. And this gives you a much better intuition to think about Noetherian rings. The key point in Noetherian rings is it prevents infinite recursion. Where recursion just means like an infinite chain of functions where at each point you use information. And sorry, just to kind of illustrate why nested ideals lead to these chains. If you had, say, the ideal multiples of 4, it's inside a multiple of 2. And this tells you that a map from Z to Z mod 4 extends to a map from Z mod 4 to Z mod 2 by just kind of taking it mod 2 again. And so why is this a useful way of framing it and thinking about it? Let's take one result. That if R is Noetherian, R mod I is Noetherian. That's just saying, if R mod I had an infinite chain of functions from it, then R has an infinite chain of functions from it. You just stick R at the front. And like, I think that's a much more natural proof than anything about like faffing around with like lifting ideals or thinking about finite generators. It's a property about there being no recursion. And when you take one extra step, you can't then start having an infinite amount of recursion. And the reason it's a property we care about at all is that not like it's a finiteness property. It's basically saying this is not a pathological case. Things are not scary, things do not break. And the reason it occurs in theorems is that the theorems are just saying there's not like stupid pathological behavior. It's like the analogy is looking at finite dimensional vector spaces, cases where there isn't infinite complexity and things don't break. So now I want to talk a bit about number theory. Which is kind of, in my opinion, the more interesting bit of the ring section. And you can kind of think about that section of course as being intro to algebraic number theory, which is an incredibly cool area of maths. And I very, very highly recommend the third year course number field, so anyone who's interested in this kind of thing. So this gets me on to lens 3, how to think about ideals, that I obliquely mentioned earlier. In my opinion, the kind of really cool way of thinking about ideals is you can actually think of ideals as the fundamental object of your ring. You can forget about elements and just think about ideals. I think this is kind of like a bit of a weird and confusing lens, and elements are really intuitive. So I'm not trying to get you to just forget about elements entirely, but what I want to do in this section is try and convince you that this is a legitimately very useful way of framing and thinking about like number theory. So why is this? What do I actually mean by this? So a bunch of the standard definitions of the number theory part of this course can be phrased in terms of ideals. So a unit means the ideal generated by U is the ring. It's like the ideal generated by 1. because U is invertible, so this contains 1, so it contains everything. A divides B is the same as saying the ideal generated by A contains the ideal generated by B. Notice that this is the opposite way around to what you'd expect. That's because being a multiple of B implies you're a multiple of A, but it's contained within that. Like, all multiples of 4 are also multiples of 2. And if A is an associate of B, i.e. A is B times a unit, then the ideal generated by A is the same as the ideal generated by B. So that probably doesn't seem like incredibly compelling. I think that this perspective really comes into its own when you're thinking about things like the kind of guts of the number theory. So let's look at greatest common divisors. So greatest common divisors are only defined up to associates. Like, if D is the greatest common divisor, then so is D times a unit. This is kind of annoying because greatest common divisor feels like it should be a unique thing. This even applies in just like actual number theory, because 5 and if 5 is the greatest common divisor, minus 5 is also in some sense the greatest common divisor. But intuitively, this doesn't really matter. Like, you just ignore the units and you think about the class of associates. And as a general high-level maths idea, whenever you have arbitrary structure that you can kind of sweep under the rug, just not care about, that suggests that there's some deeper structure hiding beneath the surface. And if only I just find a way to forget about associates. So the point of ideals is that they are the deeper structure hiding beneath the surface whenever you say something about up to association or multiple units, doesn't matter. The greatest common divisor is phrased in terms of ideals. The greatest common divisor of say A and B is the smallest principal ideal that is the smallest principal ideal that contains both of them, such that if E also contains both of them, that implies D contains E. Let's take another number theory example. The way to define unique factorization domain is to say that anything factors into irreducibles up to associates. You could have 3 in there, you could have minus 3. If you're in the Gaussian integers, you could have 3, minus 3, 3i, or minus 3i. And this gets arbitrarily more annoying the messier ring is. But if you phrase it in terms of ideals, it's just the ideal generated by 3. That's the same as the ideal generated by minus 3. You kind of just got rid of this arbitrary structure. And the true object here is ideals. But, and just to erase it again, they are the fundamental objects of a ring in a way which becomes more and more apparent the more familiar you are with rings and the more you study the number theory of rings. And to take a somewhat advanced and much deeper example, you can actually think about ideals, you can just forget about elements completely. So everything I did over here was phrasing a statement about elements in terms of ideals, but you can just not engage with elements at all. I can do number theory with ideals, because I can define the product of 2 ideals as the span of the product of elements. So this is the thing generated by products of elements. You can have things in here that aren't the product of elements if you get them by adding some things together. And this is an elementary definition, but it means if I just forget about how I define this, I can just take ideals and multiply them all together. So what does this mean if they're principal ideal domains? This is just the ideal generated by the product of the generators. And in general, if you instead have BC here, then you get the ideal generated by AVAC. So this kind of obeys our intuitions. But the reason I think this is interesting is that, so a kind of fundamental tragedy of this part of the course is that we just find this incredibly nice property called it being a UFD, but then loads of things aren't UFDs, and like, what? But actually, a lot of the things that aren't UFDs are UFDs, but for prime ideals, not prime numbers. To illustrate this, let's look at like z adjoin root 5i. So integers plus integers times root 5i. So this is not a UFD, because 2 times 3 equals 1 plus root 5i times 1 minus root 5i. And these are all irreducible elements that don't divide each other out. But you can, but it isn't UFD with primes, because because the ideal generated by 3 is the ideal generated by 3 and root 5 minus I times the ideal generated by 3 and 1 minus root 5i. And proving this is just a bash, but you can just show that these are prime ideals and that they multiply to get this. And you can do all of this in terms of these ideals. And it is there's a ton of deep math behind all this, and go to polynomials, you want a complete treatment of this, but they are actually a more fundamental object to do number theory with. And there's a really, really cool theorem you prove in the number fields course that says if you take the rationals and add in some algebraic numbers, like say root 5i, algebraic number you're inventing a root of some polynomial, then the integers inside this, so these are the integers when you add in root 5i, the integers are a unique factorization domain for prime ideals, no matter what you add in. And like, that is so much more powerful than like, you get z plus root 2i, but not root 3i, root 5i, or anything beyond that. Like, it's just so much more fundamental to how this actually works. In fact, etymologically, the reason they're called ideals is that Dedekind was studying this ring and was really sad that it wasn't a UFD, and then found out that it was a UFD if you looked at these. And so we called them ideal elements because they kind of made everything nice. Like, that's why they're called ideals in the first place. Okay, so that was like a long, not especially course relevant tangent, but I hope I've kind of, in some sense, convinced you that thinking about them as ideals is important and insightful. Again, like, use elements as well, because elements are intuitive, but a lot of statements are hard because they're naturally phrased in terms of ideals. And it's another language you can think about rings in. So now I want to talk about the classification of rings. So that's like a thing the course goes into quite a lot of detail about. Does anyone have any questions about that section before I move on? Cool. So the classification of rings, I think, is best phrased in terms of a flow diagram. So we have the lightest possible ring, a field. Like, fields are just so lovely. You then get slightly messier when you have Euclidean domains. So these are things with a norm, where you can apply the Euclidean algorithm, like the integers. You then get principal ideal domains. So that's where every ideal is a principal ideal. Every ideal looks like multiples of 2 or multiples of 3. So like Z is a good example of a principal ideal domain. The next one is a unique factorization domain. So like where the fundamental theorem of arithmetic holds. And finally you get integral domains. So that's where the product of any two things is non-zero, unless one of them is 0. Like where multiplication is injective. And so I think that this section kind of gets really messy and confusing, and it's easy to lose track of like why you care about these things and how they fit together. So I just want to kind of try and give a very high-level overview and talk about why we actually care about all of these and how they link together. So fields like, they're just obviously really interesting. Like, all of linear algebra is about studying fields. You have the ability to multiply and divide, you have 0 and 1, they're just great. So fields get a smiley face and you need no further justification. Integral domains, I think, are also really nice. Like, it's basically saying things don't get stupid. Like, when you multiply with something, you don't get 0 out. It's saying multiplication is injective, which is a really natural property to have. They also get a smiley face. And a really important property of integral domains is they live inside a field. Because you can define a field of fractions for integral domains. Like, for example, if you look at Z in integral domain, you can define Q, the field of fractions. If instead this was like polynomials, you could define the field of rational functions. And this is a thing you're only allowed to do with this integral domain. But it's actually really, really important because fields are really nice. And integral domains live inside fields. And so you can often use this field to understand the integral domain better. For example, if I want to factor polynomials in R, they live inside a field, C. Sorry, this is not a case of integral domains in the field. This is a general point about things living inside other structures is useful. The reals live inside the complex numbers. And even though the complex numbers aren't something I can talk about when I'm talking about R, they tell me things like how do polynomials over R factorize. It tells me that the only irreducible polynomials over R are linear and quadratic things. And kind of analogously, knowing this field exists is really useful for understanding integral domains. But now for like the messy middle bit. So Euclidean domains are not really interesting. They get a sad face. The point of Euclidean domains is it's a tool to find principal ideal domains. That's like the only reason you ever care about Euclidean domains. Because it's really easy to show something has a norm. It's hard to show that every ideal is principal, because that's just a really hard thing to prove. And it's like quite easy to show this implication holds. And observe that this is just a definition, and this is kind of trivial, because your norm here is everything is 1. So, though, fun fact, it's not actually the case that all principal ideal domains are Euclidean domains. You can prove, though I'm not going to, that the integers plus this is a principal ideal domain, but it's not a Euclidean domain. And if anyone's interested, message me afterwards. I'll send you a link to a proof of this. So, you know, if you ever get an exam question that says, does there exist a principal ideal domain that's not a Euclidean domain? Regurgitate this. Okay, so why do we care about principal ideal domains? So these are like way more interesting than Euclidean domains. So first off, like a bunch of really common rings are examples of these. Like polynomials over a field, the integers and complex numbers. These come up a lot. The deeper reason behind why they're interesting is that, so what this is actually telling us is that ideals in a PID are the same as, they're the same as elements. Like, you can think of every ideal as being generated by like a associate class of elements. And you can think of every element in terms of its ideals. Why is this so useful? It's useful because of all the waffle I said earlier about ideals being a fundamental object. There's also deep structure you can think about for ideals, which you can just immediately copy over to think about elements. To take one example of how this link is really important. So you can prove in a fairly boring way that PIDs are UFDs. I'm not going to go into any detail about this proof. But this is interesting because it tells me that in a PID, prime ideals are all maximal. Why? Because this statement of ideals, well, I can convert it to a statement of elements because the structure is the same and you can use one to understand the other. So an ideal is, if an ideal is not maximal, then there's something between it and the ring. So if the ideal generated by A is not maximal, there's a B so this is true, which means that an ideal contains another if the generator divides that generator. Let's just say that 1 divides B divides A, which means that A is not irreducible. And you can show that because it's UFD, ideals generated by an irreducible element are prime ideals. And so in a principal ideal domain, all prime ideals are exactly the same as maximal ideals, because being contained in another ideal is the same as having a factor. Ideal structure is the same as element structure. And this is like a really, really useful fact about principal ideal domains. For example, anytime you quotient a polynomial over a field by an irreducible thing, it's always a field because that's a prime ideal, so it's a maximal ideal. And the other key result about principal ideal domains is that the ideal generated by two things is principal. And so this is the greatest common divisor. And this tells you the greatest common divisor is a linear combination of generators, which is really useful. It's basically basically every time you use that in numbers and sets to prove anything, you can just copy that proof here. And that's why the notation exists for greatest common divisors, like ideals. And finally, unique factorization domains. I don't think I really have to justify why they're interesting. It's a really, really nice property. They just get a smiley face. Oh, these also get a smiley face. I just hate Euclidean domains. You get a smaller smiley face. And the one interesting I want to emphasize for unique factorization domains is that the definition comes in two parts. You not only have to say that things factor uniquely into irreducibles, you also have to say that all elements factor uniquely into irreducibles. But you also have to show they factor at all, and that's a really easy thing to forget. But it's important because you can actually have rings where there are things that cannot be written as a product of irreducibles. For example, if you take the complex numbers and you adjoin x to the half, x to 4, just x to 2 to the minus n for all n, then x is x to the half, you can just keep doing this until you get to x to the 1 over 2 to the n. And so this is not a UFD because x can be written as a product of irreducibles. You can always break it down further, which I think is quite cool. So you really need to remember that step when you're showing something UFD. And note that this is another example of kind of infinite recursion. So this is not Noetherian because you have this ability to go infinitely far down. And so the reason you'd have Noetherian in a bunch of theorems is it says you can't have crap like this. Cool. So I'm going to talk a bit about polynomials at the end of this talk about time, but that was the main bulk of what I had to say about ideals. So I just want to recap the important ideas in there. The reason we think about ideals is that they're kernels of homomorphisms. And that should be a really, really important part of your intuition when you're trying to think and reason about them. Noetherian means it's a kind of finiteness property. It's telling you there's no such thing as infinite recursion. And you should try and phrase it in terms of functions, because that's a much nicer way to think about it. Ideals are, in some sense, the fundamental object of ring theory. You can think only in terms of ideals. And that's a really, really deep and beautiful result. And when classifying them, fields and integral domains are obviously interesting. Integral domains live inside a field of other things. Euclidean domains are just a tool to prove principal ideal domains. These are interesting because ideals are the same as elements. The structure is deeply related. And it is a useful way to prove things you have to. And that is ring theory. Any questions? Cool. I will take a 1 or 2 minute break and then get on to the modules. For anyone who's considering leaving because they don't like modules, I think we've got a better way of teaching than the course does, so would recommend hearing me out. Looking at you, Chris. Recording going well?
Yeah.
Cool.
Yeah, get well either that much.
That's true in general because as long as the action is an injective action, it's true because G maps to an element of imitation. And so if it's simple, it's an injective. So the image of G is a subgroup of an imitation. So the size divides the size. And
We're
it's
running
over
shared
two.
modules.
Thank you very much. Sorry.
They get
It's true for an injective action. And you get injective. And you get injective action. Faithful. Yeah, faithful. And all actions are subgroups. No worries. Thanks for coming.
so next chapter is that. Yeah.
Modules time. So I think the kind of really high level summary of the section is modules are hard. So I want to begin by kind of thinking about why do we care about so why do we care about modules? So the reason we care about modules is that modules arise when you have a ring acting on something else. They're kind of analogous to vector spaces, but for rings instead of fields. You could also think of them as like analogous to a group action, but a ring action instead of a group action. And they arise like all over the place because anytime you have something acting on something else, and there's a notion of addition and a notion of multiplication, that tells you it's a module. And things with two different actions, things with two different operations, just like come up everywhere. So I think the two like really important examples of this are finitely generated abelian groups. Abelian groups in general are Z modules because you can think of an integer acting on A as going to A to the n, and like you can just show this as a Z module. Linear maps from a vector space to itself are an example of this because you can add two linear maps together and you can compose two linear maps. That looks like multiplication. And ideals are an example of this because like when you scale by elements of your ring, that's a ring action. And these are all like really important examples of modules. So secondly, modules are hard. What do I mean by this? Why are modules so hard? So as I said earlier, modules are basically linear algebra, but for rings instead of fields. So, and linear algebra is really easy. Like, I've given 4 hours about how great linear algebra. I've given 4 hours of talks about how great linear algebra is. They're on YouTube now. And so, hopefully, we have a good intuition for linear algebra, even if all you've done is vectors and matrices. And so, we want to use that intuition wherever we can. And what's the number one intuition you should have for linear algebra? Choose the right basis. I think I've said that for the 20th time now. And so we want to understand modules by choosing a basis. And a basis for a module is like exactly the same thing as for a vector space. It's something that's spanning, so it generates a set. And it's something that's linearly independent. So no non-trivial linear combination is 0. And so this feels just like linear algebra right now. But a lot of things break because multiplication is not invertible. And that's a really important difference. For example, it is no longer true that given any spanning set, there's a subset that's a basis. So late. For example, 2 and 3 generates like the integers, but no subset of this is a basis for the integers. Like 2 never gets an odd number, 3 never gets like things that aren't multiples of 3. like we lose silence, which is a really important result of understanding linear algebra, but it's actually deeper than that. If we imagine, again, just z, and we imagine a number line, say this is 0, what happens when we double this? So let's look at 2z. So with 2z, like 0 remains the same, but 1 goes over here. There's like a hole. Minus 1 goes over here. There's a hole. And so if we quotient by 2z, then we get just two things. Like we now have a loop. And this fundamentally arose because multiplication is not inversible. And so when you apply a non-inversible function, you can lose things. That's what introducing holes really means. Like, if instead I have a cube, so it's going to look like a line, then when I double that line, it looks exactly the same. Like, when you double the rationals, you can halve them again. But you can't halve the integers. And so this is an example of torsion. Torsion is when you have something like z mod 2. So you have an element that's non-zero, and you have an integral domain, but when you act on that with a non-zero element, you get 0 out. You can think of this like things with finite order in an abelian group. And a kind of really key point about modules is that the reason they're so hard is that they have torsion. So torsion is why modules are hard. Because torsion kind of captures this notion of multiplication is not inversible. And why is this such a big deal? It's a really big deal because this is like an interesting natural module, which I get by just like scaling, taking quotients, doing natural things. But there fundamentally does not exist a basis, because a basis needs to be linearly independent. But any element in here doubles to an element that isn't in there. And like, that's a really big deal. So we're going to need to be creative about dealing with this later on. And the second point about like what goes wrong is just rings are way, way harder than fields. They have so much deeper structure. For context, see all of number theory, and like the prime number theorem, and just all of the random mysterious crap, and like so many things we haven't even solved, like the Riemann hypothesis, or Goldbach's conjecture, or Fermat's theorem until about 20 years ago. And so, in general, modules are just too hard to get your head around. And so the story of this chapter is unlike our hope for normal maths, where we kind of start with a really general thing and try and engage with it and play with it. What we're actually going to do is run away screaming from the general case and study the easiest possible cases and try and build up these really easy cases into understanding harder and harder things. It's like a complete perspective shift, because we're not trying to understand complete structure. We're just trying to understand anything at all and it's only build up. So the kind of roadmap that we're going to follow is we're going to understand R to the n, then we're going to understand submodules of R to the n, then we're going to understand those again, because we failed the first time, and then we're going to understand finitely generated modules. And these all build on each other. So let's warm up. Let's just start with R. Like, R is the best module ever, because what's the basis? Natural question can always argue it's not understanding a module. That's just what? Like, yay, this is great. We understand R completely.
What's the negative one?
And instead it was a unique basis. So, yeah, and like, our number one goal at all points, so what I'm going to write up here, the key point is want a basis. Because a basis is like the lens you understand your space through. And it goes from this messy, abstract thing to like a really simple thing you understand. And yeah, like R is really easy. But a natural thing to want from modules is that a submodule inherits structure. So we want submodules of R to be nice. And what's a submodule of R? That's just an ideal. So we want ideals to be nice. And if R is like not a print by domain, like say R is z with x added into it, then you can get annoying ideas like 2 comma x. We go from a one-dimensional thing to a two-dimensional thing. Like, what? This is not working. So, point 1, I'll actually write that over here. Point 1, we want R to be a principal ideal domain, because intuitively, principal ideal domains tell us that submodules have some nice structure. Okay, so the course actually teaches it for Euclidean domains, but like the proofs basically just work the same.
Wait, aren't ideals exactly the submodules of R?
Yes.
Okay.
Yes, like we're choosing principal ideal domains so submodules are nice in this special case, in the hope that'll work in general. Spoilers, it will. Okay, so we want R to be a principal ideal domain. And so we now understand R and we understand submodules. So the next step is R to the n. So what does R to the n look like? It has a basis. Yay. Like, it's just nice. The basis is like 1, 0s, 0, 1, 0s. Like, it's just the same as like C to the n in general. It looks like a vector space. This is great. So now, hopefully, submodules are going to be nice as well. And I think this is a lot less obvious. So I'm going to take a specific example to try and illustrate how we understand this. Let's look at a submodule of z squared. So generated by these. And kind of the point of ideals, or submodules generated by things, is that you can manipulate these and it's still the same submodule. So it's kind of like solving equations, because it's linear algebra, so like, let's just do that. We can subtract this from this to get 2, 2, and then we can subtract 2, 2 from everything to get like 0, 1, and then you can subtract 0, 1 and 2, 2 from everything to get nothing. And so this submodule has a really nice basis, 2, 2, 0, 1, and you can kind of observe that it's a basis because it's a lower triangular thing. And the general case of studying submodules of R to the n is just applying this idea in general. So what do we do to find 2, 2? We said, I've got 4, 6, and 8 on the top. I want to find the smallest possible thing, like the greatest common divisor. And it's a PID. So linear combinations are going to give me the greatest common divisor. That's like the point of being a PID. So if I project M onto the first element, that's a submodule of R. So it's a principal ideal. So it looks like this. And this means that there's something inside M which looks like D followed by some stuff. And D divides every first element. Like 2 divides all of these. Which means that everything in M is something times V plus something with a 0 on top. And so if you, like, we can now just say V is a basis element, and the stuff that's left lives inside R to the n minus 1, and we just induct. So we've done this proof in generality. We've just constructed a lower triangular basis, and we've made it so it's lower triangular, so we know it's a basis. So the point is, like, this has a basis, and its size less at most n. You can have something that's like worse. You can have something that's strictly less than n if, like, say d is 0, because then you don't need to do anything at all. You just ignore the first element. So we've just shown that every submodule of R to the n looks like R to the k. So we're done, right? No, we're not, because we haven't distinguished between 2z and 3z. So these are both submodules of z. So just R to the 1 if R is our ring. And these look different. Like, if you quotient by this, you get z mod 2. If you quotient by this, you get z mod 3. But our understanding right now is just too basic. all we know is that these both look like Z. Like, this is too simplistic. We need to go deeper. And why are these two things different? They're different because here the basis is 2, here the basis is 3, and here the basis is 1. So we understand the basis of 2Z in terms of the basis of Z. We understand the basis of 3Z in terms of the basis of Z. And that's how to distinguish the two things. So the high level point here is to understand submodules of R to the n, you want to simultaneously choose a basis of R to the n and a basis of your submodule, where they're kind of nicely phrased in terms of each other. And like, that's what we did here. And if you've been paying attention, this hopefully sounds quite familiar, because that's what Smith normal form's about.
As in, you don't just understand the submodule up to isomorphism, you also understand it in relation to its ambient module.
Yeah, exactly. Again, like, this is I think this is a really insightful example, so just stare at this to let this idea make sense. So, formally, what are we actually doing? We're saying a submodule of R to the n looks like R to the k. Let's just pretend k is n by just adding in some 0 elements. This means that there's a map from R to the n to R to the n, where the image is n. So like, this map just says, I've got a generating set. I'm going to take in a vector from R and make that a vector of coefficients for my generating set. Like, if m was 1, 0, 1, 1, this map would send AB to A plus B over B. Like, A times this thing plus B times this thing. So, and the cool point is that this map is a matrix. You can represent this as a matrix because these both have natural bases. So it's like an n by n grid. And we can manipulate the basis of R to the n and the basis of the other copy of R to the n. I'll call these U and V to make it clearer their different spaces. But W. This is the space of coefficients. This is the space the module lives in. They're like fundamentally different places. And so I want to try and choose a different basis of these two things. That's just, choosing a different basis is like applying an invertible matrix on one side. And that's the same as a row or column operation. Like, swapping two rows is like swapping two basis elements. Adding a multiple of one to the other is like adding a multiple of that basis element to this thing. Scaling one by a unit is like scaling a basis element by a unit. So the point of Smith normal form is that if I have any linear map, like any submodule of R to the n, and it's over a Euclidean domain, or actually a principal ideal domain, but I'm not going to get into why the proof happens to work in both cases. You can manipulate the basis of U and the basis of W so that this matrix looks like D1 until Dn with zeros everywhere else, where D1 divides D2 divides Dn. And what's the point of this? The point is that a matrix having this form says I can choose a basis of U and I can choose a basis of W so that it looks like this. And that's really saying there's a basis of U, the space of coefficients, which maps to D1 until Dn as coefficients of the basis of W. So the basis of W is W1 to Wn. And the basis of the image is D1 W1 until Dn Wn. Like, I've chosen a basis of the image, basis of M, and chosen a basis of R to the n, and they're simultaneously a nice basis of this and of this. So I understand the structure of this module in terms of the structure of the parent module. I'm going to say that again, because this is like a really, really important, I think, quite subtle point. The key is, the key point here is Smith normal form is about simultaneously choosing a basis. And, like, think we can now just rest. Like, we have conclusively understood what submodules of R look like, and it's a really nice form. And we now understand the difference between 2z and 3z. And the reason I'm kind of saying all this again and again is I think this is a really important and subtle point. So like, if you have any questions, please do ask. And I think this bit of the course is like not well taught at all. So yeah, we've chosen a nice basis. So we are now most of the way through our roadmap. It's simultaneously a nice basis. So like M just looks like d1 something, d2 times something, until dn times something, which is like a really, like, so much nicer than what we had up here. And so now we finally get to the thing we actually care about. So finitely generated modules. And so this is like the point where things become scary, because finitely generated modules allow things like torsion. They allow things that like having holes in my space, and that's annoying, because it means I can't choose a basis. So all of my intuitions and logic so far feel like they just break. But the clever idea is figuring out how to link this harder thing to the easier things I understand. And a module is finitely generated means that there's a surject, if there's n generators, there's a surjective map, the larynx means surjective, from R to that module. I'll call the module P. What's this map? This map is just taking a vector with coefficients and making those the coefficients of the generators. And this is important because we now can understand our module in terms of what this map looks like. And this map lives in R to the n, and we understand R to the n. And by the first isomorphism theorem, P is isomorphic to R to the n, quotiented by the kernel. And the kernel of this HOM is a submodule. And the way to understand submodules of R to the n is simultaneously choose a nice basis. And so, like, choosing a basis doesn't affect what this thing looks like. A basis is just a lens to see the space through. It doesn't affect the underlying structure. And so, this looks like kind of R to the n mod by d1 times something, d2 times something, until dn times something. And hopefully it's pretty clear that this is going to be, the first thing is something mod d1, the second coordinate is something mod d2, etc. So this looks like R mod d1r, or sorry, phrase it like this, until R mod dn. And we now perfectly understand finitely generated modules, because we've slowly and laboriously built up our understanding from simple building blocks to like this beautiful, complicated like end goal. And this is really important because these come up everywhere. Like abelian groups are modules over a Euclidean domain. They're like Z modules. And so all abelian groups look like Z mod a bunch of stuff multiplied together. And so all abelian groups look like Z mod, like the product of Z mod something times Z to the K, where the Z to the K is just when the D's are 0, because R mod 0 is just R. Like, modding is just setting something to 0. If what you're setting to 0 is 0, it does nothing. Okay, so let's kind of try and do an example, because I think this is like a difficult thing to get your head around. So let's look at an abelian group. Like G has two generators, A and B. I'm going to give it a bunch of constraints. Where 0 is just the identity of my abelian group, because like I'm using addition. And how do I understand this? So if I didn't understand modules at all, I would just kind of try and solve these equations and get them to a nicer form. So does this equation matter? No, it's implied by this one. So I can just forget about it. Does this equation matter? Yes. But I can subtract this one from it to get the new constraint, b equals 0. And with this constraint, I can simplify the first thing to 2a equals 0. And so this group is just z mod 2. But everything I did was kind of like fiddly and arbitrary. So let's think about the deeper math behind what I just did. I had a bunch of constraints, so a bunch of equations, and these equations were kind of arbitrary. Like, I had something that didn't matter. If I added on a new equation based on these, it didn't change the underlying group. And again, high-level maths idea. When you have arbitrary structure, you know it doesn't matter, and you can manipulate it to a nicer form, that suggests there's some underlying structure. And the underlying structure that has emerged from our study of modules is that these constraints are the kernel of the map from z squared to my group, where I map like c and d to the coefficients. And so the kernel is generated by the vectors 2, 3, 4, 6, 2, 4. This is a matrix, so I want to put this into Smith normal form, which is like choosing a basis of the constraints. But everything I did about here, just manipulating equations, was just finding a basis for the equations. Like, that's what finding a basis is really about. It's about manipulating linear things into a nice form. And the Smith normal form of this is just 1, 2. And that's exactly represented by this. Observe that manipulating equations is like changing the constraints. Manipulating the rows is like changing the generators. And so what I've done to get into Smith normal form is swap the roles of A and B. But in general, like I could replace the generator A with the generator A plus B, and that'll be perfectly useful. Yeah?
I'm just wondering, wouldn't it be like 2 and then 1 because it's B that's 0 and 2A that's 0, not the other way around?
So the point is Smith normal form always needs to have this divides this. And so what I actually do is I swap the two rows around. Like, I change the roles of B and A because I want to have it in this canonical, unique form. And it kind of doesn't really matter what order the generators are in. It's still the same underlying group. But, yeah. So, that is the point of modules. Like, it's all about understanding constraints. Is the constraints are kind of arbitrary. We really want to solve a system of equations. And that's what linear algebra and Smith normal form is about. It's about giving a really general statement about how effectively you can solve equations. And so, yeah, that is the story of modules. On a more kind of exam relevant point, a really, really common question is like, find the Smith normal form of a submatrix. So I just want to briefly talk about how you actually do this. And a really important point for understanding Smith normal form is this notion of fitting ideals. So the K-fitting ideal is the ideal generated by the determinants of K by K submatrices. And so for example, if I had the matrix 1, 2, 3, 4, 5, 6, the fitting ideal would be generated by the determinant of this bit, the determinant of 1, 3, 5, 6, and the determinant of 2, 5, 4, 6. So submatrices I have to be like a continuous block. Why is this an interesting object? This is an interesting object because it's preserved by changing your basis. And like, that's kind of you can just kind of show that as a bit of a bash, but the point is more, fitting ideals get to the underlying structure of the space. And the reason that is that if you write a matrix in Smith normal form, maybe with some more zeros over here, then the fitting ideals, the K fitting ideal, is just the thing generated by the product of D1 to dk. Because the only submatrices with an interesting determinant are along the diagonal. And if you're further down the diagonal, because D1 divides everything else, the smallest possible determinant is where D1's in there, and D2's in there, etc. And so if you know the fitting ideals, you know how, like, D1 times D2, D1 times D2 times D3, etc., which is enough to tell you what the Smith normal form looks like. And this is also how you show it's unique. Like, you can define these fitting ideals and just show they're a well-defined object. The useful point for like exams is that if your matrix is sparse, finding the fitting ideals is really easy. And the first fitting ideal is also really easy. It's just the greatest common divisor. And the point, which I think is more subtle, is that you can switch from doing row and column operations to looking at fitting ideals mid-question. Like, often you got, say, a 303 matrix, and you find D1, and you make D0, and then you got to do row and column operation on this. You could just look at the determinant of the 2x2 matrix, look at the DCT, and then that's the Smith normal form. And it's really worth having in mind in the middle of a question, is it easy to switch? Because that can actually be quite a big speed. Okay, so to recap again, because I think this is like the most complicated section of this talk, modules are hard. You want to understand modules by choosing a basis. And the reason they're hard is because you have this notion of torsion, which is a really fundamental idea, because it comes from multiplication not being invertible, and it prevents you choosing a basis. Torsion are things like Z mod 2. And because they're so hard, we can understand them by starting from really easy things and kind of exploring out, rather than starting from hard things and simplifying. And we show that submodules of R to the n have a basis. They look like R to the k. We then build on this and simultaneously choose a basis. And Smith normal form is telling us how good a basis we can choose. And to understand finite generation modules, we see that it looks like R to the n mod some kernel. And that kernel is a submodule. And we understand submodules. And choosing a lovely basis tells you what this quotient looks like. And if you get a question about general modules in the exam, it's probably terrifying, so run away. But if you get a question about like PIDs and modules over PIDs, you can probably use one of these fundamental ideas to just do it really nicely. Because we're building powerful tools and powerful machinery for understanding. Cool. So that is it for modules. Are there any questions? Cool. If not, I'm going to try and quickly go through the key points of the next chapter on polynomials and try to spend 2 minutes. So, chapter 4. Polynomials. So here I want to kind of look at polynomial rings, how they actually work, how to understand them, and kind of why they matter, and why you get random crap, like normal form falling out of looking at polynomials acting on a vector space, like what? So the reason we care about polynomials is polynomials are what happens when you take a ring R and you extend it. You add in another element x, and you know nothing about it. So like, what things does x generate? If x multiplies an element of R, that's just a coefficient. If x multiplies itself, you get a power of x. And so the things that get added when you add in a magical new element are just polynomials. So the reason they're an interesting object to study is a really common thing to do with rings is to take in a new element. Like the complex numbers is the reals plus I. And the way to understand adding in a new element is to look at what happens in general and then add a constraint. So this is the same as R with x in it, mod x squared plus 1. Because this is how you define I. This is the constraint you have in. And it's just the general case of extending, mod some constraint. And like, that's why polynomials are interesting. And this is like a deeply, deeply fundamental question. And it's like, this is what the second year Galois theory course is all about. Like, what happens to polynomials when you add things in, and how is their structure affected? So, next subchapter, structured polynomials. So, here the really clever idea and the key point is that we care about integral domains, and integral domains live inside a field. Like, it lives inside a field of fractions. Why is this interesting? It's interesting because it means that R of x, polynomials over an integral domain, live inside polynomials over its field of fractions. And polynomials over a field are really nice, because this is Euclidean domain. So it's a PID, so it's a UFD. And the point of basically all of our understanding of the structure of like polynomials over an integral domain is they live inside this really, really nice thing that's way nicer than just arbitrary integral domains. So how can you use this beautiful ambient structure to understand them better? And so like the key point is kind of how does living in the field give you niceness out? And in some sense that's like the fundamental question part 2 number fields is about answering. Like Z lives inside Q. How does understanding Q tell you about Z and things related to Z? So like this is deep enough point you can build an entire course around this. But in brief,
fields of fractions.
Yeah, like Gauss's lemma tells you that R UFD implies Rx UFD. So the UFD property is so strong that adding in a magic element preserves it. And how do you show this? You basically just show this by this core idea. Like R of x is an integral domain, so it lives inside f of x. And so you need to use the fact that f of x exists to study this. And the key lemma is that p and q primitive, so the greatest common divisor of the coefficients is 1, implies their product is primitive. Well, these are polynomials. And like, proving this is like a bit messy, and it uses the fact that there's UFD a lot. But when you have this, like, Gauss's lemma is kind of obviously follows. You define this notion of the content of a polynomial as the GCD of the coefficients. And then when you have, and so the polynomial is the content times a primitive thing. And so given any polynomial, if it's irreducible in, like, if it's reducible in f of x, a UFD, then you can just scale up to R of x, understand it there by using the scaling in this key lemma, and that means it's reducible in R of x. And like that's all Gauss's lemma is saying, and that's all like a lot of the polynomial stuff in this course is saying. And an important thing, a kind of interesting consequence I think is worth highlighting, is this tells me that UFD extended is a UFD. So, and a natural question to ask is like, how common is this thing? And it's not true for stronger rings. So it's not true for principal ideal domains. And this is kind of our first inkling that UFDs and PIDs are fundamentally different things. Like, this tells us how to build UFDs that aren't PIDs, because if you pick a PID and you take a polynomial ring, it's a UFD, but it's not a principal ideal domain. And that's how you find an example of something that's this, but not this, Z of x. But I think it's worth highlighting when things that feel really similar diverge. And the additional cool point of all this is that if you do have a principal ideal domain, we have this great lemma that if R is a PID, then prime ideals are the same as maximal ideals. And so, and a prime ideal, because ideals are the same as elements, is something generated by an irreducible. And so, if you take f of x, so it's Euclidean domain, so it's a PID, and you quotient by a right polynomial, this is a field. Because prime ideals, like primes generate prime ideals, which are also maximal ideals, and so the quotient is a field. And that's like a really, really useful property, because it just comes up loads. Like R of x mod by x squared plus 1 is complex numbers, that's a field because of this. And this is true when you add in anything algebraic to any field. Like if you add in the root of x to the 7 plus 5, if that's an irreducible polynomial, then to the rationals, then that's a field. And okay, so that's enough of the kind of ringsy bit of polynomials. Next, I want to talk about the Hilbert basis theorem. So the Hilbert basis theorem basically says polynomials over a Noetherian ring are Noetherian. So why does this make intuitive sense? This makes intuitive sense because Noetherian is a finiteness property, and polynomials are kind of fundamentally finite. Like, you can't recurse down in a polynomial far because everything has finite degree. And recursion in a polynomial is kind of going to smaller degrees. So what this theorem is saying is that you cannot, like, you stop, it's basically saying finite times finite equals finite. Like, gluing these two finite notions together can't give you something infinite. And so it's like a really intuitive thing. And there are like several really lovely abundance proofs of this. So the kind of key notion here is that when I say polynomials don't allow infinite recursion, what I'm really saying is that x to the k divides x to the k plus 1. So understanding smaller terms tells you something about the larger terms. Like, if you have an ideal inside R of x, I think the notation is like this, then, and if some polynomial is in here, then x times that polynomial is also in there. Like, you can't just think about x and x squared and x cubed independently. If you could get infinite stuff. And the proof is kind of just formalizing this notion. We want to show it's Noetherian. So you want to try and construct an infinite chain of ideals and see where it breaks. And the way to do this is by saying, I'm going to start with some ideal and try and build a generating set. And I want to try and make a small generating set. Because I don't want to choose like x to the 5, then x to the 4, then x cubed, then x squared, then x, then 1. I would rather start with just 1. So I'm going to choose the smallest thing inside this ideal, the thing of smallest degree inside here that I haven't already made. So I want to build a generating set inductively, where n plus 1 is the min degree thing inside I, which is not inside Jn. And the kind of cool idea, sorry, these are polynomials, so I'll call them P. And the kind of interesting idea is that because the degree is increasing, the leading coefficients of these must not generate the leading coefficient of this. Because if I had, say, like x, if I had, say, 3x, 2x squared here, the leading coefficient generates 1. And so x squared is also inside this ideal, because 3x squared minus 2x squared equals x squared. Like, the leading coefficients generate 1, and so you can't have leading coefficient 1 in the stuff that doesn't appear. And this is important because it means that if I just read off the leading coefficients of each of these polynomials, that must generate an infinite generating set of an ideal inside R, but R is Noetherian, so that's impossible. A kind of harder, but I think really, really nice alternate proof of this is if you take an infinite chain of ideals, you can write a grid, like indexed up like 1 on each side, where the entry inside here are the ideal generated by the coefficients of quadratic terms in I1. The things over here are like the ideal generated by the coefficients of degree 4 terms in I2. And these are all ideals. And you can show that they're nested in both directions. And the proof is basically just saying, I can't have infinite recursion this way. I can't have infinite recursion this way. And so I can't have infinite recursion in either direction. Exercise with reader. Finish this proof. It's a really nice proof. And the final point I want to talk about, which I'll let you all go home, is like, what do polynomial modules look like? Kind of culminating in how does dual normal form actually work? So, question 1. We want to study linear maps. Why the hell are we talking about polynomials? So, what I'm going to end up doing is saying that fx acts on a vector space V as, like, sorry, let's call this C, just because I don't really care about the context on this here. by, like, ZV is just the scalar, and x dot v is a particular linear map of v. So, like, what? This seems really on both faces magical. What's going on here? What's really going on is I want to study linear maps on V. So those are endomorphisms. And like they're functions which take in V and spit out V. And these have a natural ring structure because they have two operations. I can add two endomorphisms together to get a new endomorphism. And I can compose two endomorphisms to get a new endomorphism. It looks like addition and it looks like multiplication. Annoyingly, multiplication isn't commutative, but like I'll cross when I come to it. And so I want to study endomorphisms as a ring, but I only care about one linear map. I care about alpha. Alpha is the interesting linear map for me. And what's this? And I also have to care about the identity. So, like, I care about these. And so I want to forget about all of the endomorphisms, apart from what I need from these two things. So I generates like the complex numbers because I should allow scaling. And A is kind of, alpha is like, I'm extending the complex numbers by adding in a new element. And that's what polynomials are fundamentally about. I have a ring that I care about, and I add in a single new element and I see what happens. And so studying how a particular linear map acts on a vector space is all about studying how does this act on the vector space. And this is going to be polynomials in C, mod some constraints. Like for example, if the minimal polynomial of alpha was alpha squared minus 1, this would be mod alpha squared plus 1, say. This would be mod x squared plus 1. But I don't really care about the mod part, because acting is just a function from this ring to functions from V to itself. And quotienting is just like stepping back one. So I can just think of this as a CX action by mapping CX to C alpha, and then C alpha x on V. So that's why I care about polynomials, to understand linear maps, because what I really care about is scalar maps, so complex numbers, and a single extra thing. And when you care about a ring, and you want to care about a single extra thing, and you want to see the smallest ring it generates, that looks like a polynomial ring. That's why you care about polynomial rings at all. And that's like the entire point of this section, which I do not think was emphasized enough in the course. And yeah, so I want to study CX actions, and oh, hooray, this is now commutative, because I only care about one linear map and scaling, and these all commute with each other. So I can now apply all of the ideas of this course. And so this is a linear map. This is like a PID module, or an ED module. So I can apply the fundamental theorem. And the clever idea I kind of skipped over earlier is that if you have a unique factorization domain, and you have A and B co-prime, and you're modding by AB, that looks like R mod A times R mod B. Kind of the Chinese who made the theorem applies to rings as well. And the reason I'm bringing this up is that when we apply Smith normal form and the fundamental structure theorem to like polynomial modules, we end up with V looks like C of x mod D1 until C of x mod Dn. And these all divide into each other, but that's kind of a bit boring. What I really want is kind of prime powers of polynomials, because they're easy to deal with. And so I can just break this up into prime powers. But what does a prime mean in CX? That's the same as an irreducible. And this is algebraically closed. All polynomials factor into linear bits. And so I can write this as CX mod x minus lambda I to the ki, some over things. Observe you're never going to get CX mod 0 because that'll be infinite dimensional. I only care about finite dimensional things, so I don't care about that. And why is this interesting? This is interesting because, so I just found a particular ring, like a particular space of polynomials, where where multiplying by x looks really nice, because I can choose a basis of this. Like basis 1 x minus lambda until x minus lambda to the k minus 1. Call these v0 until vk minus 1. And now my linear map on each vector is x times that polynomial. So that's lambda times vi plus vj plus vi plus 1. Like if I multiply x minus lambda by x, I get lambda times x minus lambda plus x minus lambda squared. And so I can now kind of forget about the polynomial bit, because Cx acts on this ring. And so C acts on this ring, because C is like strictly smaller and less interesting. And a C module is just a vector space. So what I've just done is found a way of breaking my vector space into bits where they're just different vector spaces, and my linear map acts on them nicely. Like these are invariant subspaces. And I've just found a really nice basis for when I act by my linear map and complex numbers. So what I just found is a basis where my linear map sends each thing to a scalar multiple of itself plus the next one. And like, that's Jordan normal form. And the kind of key to understanding Jordan normal form is it's saying a linear map looks like scaling plus a nilpotent bit. Like it shifts it along by 1. And like, that's what this is saying. X is lambda scaling plus x minus lambda. Lambda scales, x minus lambda moves 1 along. And so if you write this as a matrix, it looks like the point is studying the structure of how the linear acts on the thing and applying this really powerful general theorem gave me a lovely basis. And that's like the point of Jordan normal form. And like the same thing kind of applies when you're studying other polynomial domains, like R of x or Q of x, but they're less nice because the irreducibles are less nice, so I'm not going to talk about those. And what's Cayley-Hamilton for rings all about? Cayley-Hamilton for rings is saying, rather than looking at x as a kind of thing that acts upon it, I'm going to look at x as entries of a matrix. I'm going to make entries of my matrix polynomials. And I'm going to define xi to act as my linear map acts. My linear map just has entries in my ring. And the reason this is kind of interesting and funky is that I'm inventing a new thing that behaves like something I already understood. So I now have 2 ways to write the same map. And whenever you have 2 ways to write the same thing, it means that the difference is the 0. Like, that's why kernels represent things that get sent to each other. When 2 things get sent to each other, their difference gets sent to nothing. And so xi minus a is the 0. And by kind of magical trickery, if you like look at these weird things called adjugate matrices, that's just the determinant times the identity. The identity obviously doesn't send anything to 0. And so this polynomial, this is a polynomial on x, that sends every single thing to 0 because this map is redundant, it sends everything to 0. And like, that's kind of why Cayley-Hamilton works. There are some subtleties of people I haven't like quite figured out myself, but you're expected to do this for exams, and like, that's what's going on. You just invented this new way of representing an old thing you already understood, so the difference does nothing. And like, that's what Cayley-Hamilton's about. Because if you interpret this polynomial as a polynomial linear map, then that's just what it does. And finally, a kind of typical exam question, especially, I mean, even more in lineage than GRM, is how to find Jordan normal form. And a really useful trick there is to observe that if the algebraic multiplicity of the eigenvalue, so is at most 3, so like the kind of number of times it appears as a root of the characteristic polynomial, the number of times it appears as a root is the total size of all Jordan blocks with lambda on them. Like, if you had lambda, 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 if you have this, algebraic multiplicity is 3, and there are 2 blocks. and each block has exactly one eigenvalue in it. So the algorithm is car poly to get total size of blocks, solve equations, find number of eigenvalues, and if the algebraic multiplicity is almost 3, this exactly tells you what dual normal form looks like. And that's just like quite fast, and you're basically never getting a question where algebraic multiplicity is more than 3. But you do get a question about algebraic where the total size is like 4 by 4, but there's 2 eigenvalues. And to work in ring, you can just do this. So, yeah, to recap the important ideas in there, the entire reason we study polynomials is that what happens when you take a ring and add in a new element to it. Like, just what does it do? And like, that's a really important question to answer. Integral domains live inside a field of fractions, and polynomials of a field are really nice, and you answer all of the questions by just relating to this underlying field. For the Hilbert basis theorem, we're just saying finiteness times finiteness is finiteness. You can't invent recursion with two things that don't allow recursion. And the point of dual normal form for polynomials is we want to allow, like, we want to look at how endomorphisms act. That's like taking the complex numbers, scalars, adding in a single new thing. So it looks like a polynomial. We use this to find, in the structure theorem, to find something that behaves nicely under our polynomial. And then we just forget about the x part. Well, we now got a vector space that behaves nicely under our map. And like, that's the point of dual normal form. It's about finding invariant subspaces and choosing a basis where things are nice. And we're just applying this incredibly overpowered algebraic technique rather than the pretty Len algebra I gave in my last talk to just smash it. And that is my talk. Thank you very much. Any questions? Cool. I mean, feel very free to come up to me after if you have any questions. Thank you very much for coming again. I will be putting a feedback form online, and I would love to hear anyone's thoughts. Even if you have no criticisms to give, I like hearing what worked well and what didn't, and what people liked. I really like hearing if people got any value out of this kind of thing. And thank you very much for coming again. I hope the first year's got something out of it as well. And yeah.